Hello, the second laboratory session is devoted to regression problem and ensemble algorithms. Purpose of the session is to study ways to solve the problem of building a regression model using machine learning algorithms. It is proposed to use several regression models for the simplest decision tree to ensembles of trees in the laboratory session. The problem of forecasting the generation power of a solar power plant based on meteorological data is considered. We need to build a machine learning model to predict the generation using input parameters, features. The regression model will look for and create the relationship between the target variable y and the input factors x. Before starting to write code, I want to give a brief description of the bias variance problem and ensemble methods and models. In the lecture, you considered the problem of overfitting and underfitting of machine learning models. The same aspect can be viewed from the other side as the bias variance problem. Bias is the difference between the predicted values and the true values on the training set. Usually, high bias points to underfitting. Variance is an error due to sensitivity to small fluctuation in the training set. High variance, as a rule, indicates overfitting. We can estimate variance level using the difference between model accuracy during training and validation. In this chart, you can see examples of training and validation of these different models. Each model was trained 4 times using 4 training datasets as the original dataset with small fluctuations. In this case, in the first case, the accuracy is low, but results are stable. The difference between results between accuracies is low. It is underfitting. Next, in this case, the accuracy on training sets is high, but the results are unstable. The results are unpredictable because model shows very different results on validation set. The last case is balanced. The accuracy for training set is quite high and for validation sets too, and the results are stable. Usually, the more complicated a model, the lower bias and higher variance. And so, we need to find optimal or near to the optimal configuration of a machine learning model. If bias is high or higher than variance, we can increase the model complexity. But if variance is the main problem, then we can decrease it. An effective way to achieve balance and improve both bias and variance at the same time is not tuning a model, but connecting the models into a system, into an ensemble. It is possible to create a powerful, robust model as a system of weak models. This picture is just a symbol of a weak individual model. There are 3 main methods to create ensemble: bagging, boosting, and stacking. Let's consider only bagging and boosting. For boosting, the first step is creation multiply random subsets of the dataset, as you can see, for example. Next, we need to use each subset to train an individual model. And after that, we can combine outputs of individual models as one powerful model, as a single ensemble. And as a rule, bagging decreases variance and overfitting of individual models. It means, for example, if you have model with quite good bias, quite good accuracy on training set, but accuracy on the validation set is low, or you have high variance, then you can increase complexity of this model and apply bagging to create ensemble of several individual models. And the commonly used realization of bagging approach is random forest. It uses bagging, and as weak model or individual model, this approach uses decision tree. Next ensemble method is boosting. First of all, we need to create the first weak model using all training data without splitting as for bagging. Next, we need to save the errors of the first model. After that, we can create the next weak model taking into account data and errors of the first model. And after that, we have a small ensemble of two weak models, and we can use it to calculate accuracy, to calculate new errors. So on this step, we use errors of the ensemble. And we need to repeat these steps for each new model. As a result, we will have ensemble of several weak models, and this approach, as a rule, decreases bias and errors of individual models. It means that you have low accuracy on training set, you have high bias, then you can apply boosting to improve accuracy, and instead of increasing complexity of models, you can apply boosting to create ensemble of these weak models. There are several commonly used realizations of the boosting idea. For example, adaptive boosting or AdaBoost. It learns from the mistakes by increasing the weight of data points on which the model was wrong. The next way of realization boosting idea is gradient boosting. It learns from the mistake, try to add a new model so that adding it minimizes the ensemble error. Now let's switch to our task. This table shows a fragment of the initial dataset. The dataset was cleaned and it is ready for applying machine learning. The dataset is provided as an Excel file, table, and contains information about the generated power of the solar power plant at hourly intervals. In addition to the actual generated power, these tables provide us information on the observed weather conditions, namely how of the day, day number, angle of solar declination, solar time, solar radiation, flux density, cloudiness in percents, atmospheric transmissivity in percents, temperature in degrees Celsius, humidity in percents, wind speed in meters per second, and actual power generation kilowatts hour. The first step is reading the input file and checking the file format. Next, we will analyze feature using visualization tools. After that, we will split the dataset into two parts. The first part will be used for cross-validation and the second for testing. And we will consider several models from the scikit-learn library and select hyperparameters of the models. And the last two steps are testing the selected model and save it to a file. Okay, let's start programming, and the first step is importing models. NumPy, pandas, and for data visualization, I will use Seaborn library, and part of matplotlib library, and also I import several functions from Bokeh library. This function shows that we want to create visualization object of this library into notebook. And of course, we need to import models for machine learning. But also we need import several useful tools. For example, submodel of scalone model matrix and cross-validation. And now we can import machine learning methods, models. This library provides several large groups of machine learning models. For example, linear model. We will use linear regression as the simplest machine learning model. Next group is trees. Decision tree classifier, decision tree regressor, and of course, ensemble models. Add a boost, and as example of bagging, we will use random forest. I have uploaded the file with data, our input dataset, and now we can read it using pandas. It's Excel file. Oh, I think that I forgot to run this code. Okay, let's check our data. And check types of each feature. It shows us that all columns are in numerical form. But also I want to check gaps. As we did it during the first laboratory session. Using the function is null and summarize missing values to calculate statistic for each feature. Okay, you can see that there aren't gaps, so we can deal with this data without preprocessing. And you can see the correlation coefficients between all pairs of features. To do it, we need to create figure for drawing, and we can point out size. And for matrix of correlation coefficients, I use Seabol library heat map. And to calculate these coefficients, we can use the pandas function core. And we can specify parameters of visualization. For example, color map, maximum and minimum values for heat map. And so on. And also format of text in this matrix with 2 digits after decimal separator. Okay, of course, we need to be careful. Okay, and now you can see that we can analyze correlation coefficients between each features and between our target variable generation and all features. For example, you can see that the most important features is solar flow because it has high correlation coefficient with generation and also transparency. Okay, and let's build an interactive graph of generation on which we can enlarge the required areas. To do it, I will use Bokeh library. Again, first of all, we need to create figure to visualization and point out size of it. Next, we can add points, markers, using the property scatter. And we can use NumPy function arrange to create timestamps or to create indexes for horizontal edge. Then we need to point out data and also we can use arguments such as line width, color, and add legend. Okay, and fix mistakes. To show this object, we need to use the function show. Okay, and we can change this. And we can use about the same code to connect points. This visualization object is interactive, so we can select part, we can use different types of zooming. Okay, next sample is visualization Scatterpro plot to show dependence between the target variable and a feature. We need to again create figure, and we can just copy and paste arguments. And use the same function scatter, but now we specify two variables, for example, generation and transparency. Without additional parameters, okay, you can see that we can observe the dependence, but of course, using only transparency as input feature, we cannot create model with high accuracy. Let's consider other feature with high value of correlation, solar flow. Okay, we can conclude that using one feature cannot get us model with high accuracy, so we need to create model taking into account several features, maybe all features from our dataset. And in addition, I want to create histogram. I will use Seaborn library to do it. Histogram for generation. As you can see, a lot of points, a lot of samples have about 0 value of generation. It is not very good for our visualization because we cannot analyze all other parts. So we can use selection with condition, and we can add our condition to remove all samples with low value of generation. This part of the code select part of data frame, and after selection we can point out our column generation. Okay, and now the visualization result is good enough for analyze, and also we can, as a last sample of visualization, we can create box plot. To do it, I will use pandas functional. Okay, and now again we have a problem with generation, because due to high range of generation, we cannot analyze all other features. Let's fix it. We can just select all rows, but without the last column. The last column is generation. Now, as you can see, we can analyze features, and we can conclude that there are not obvious outliers, errors. It means that now we can apply machine learning methods to solve our regression task. And first of all, let's fragment the dataset into two parts. The first for training and validation, and the second for final testing. And to make the task closer to the real one, not an arbitrary part of the set is taken into testing, but a 20% part that refers to newer data. First of all, we need to calculate position of splitting point. To do it, we can use count of samples in data frame and multiply it by 0.8 to split 20% as testing part. And next, let's create train val part of dataset from the start from the first row to this position, this point, and all columns except last. And why train val? It is only values of generation. And for test part, we should select opposite part of our data frame from this point to the end to the last row of the dataset. And only the last column generation as y as output target variable. And we can check shapes, dimensions of our objects. Of course, we need to apply conversion from float number to integer after multiplication. Okay, now you can see that we split our initial dataset, and now we have part for training and validation, and also we have features and target variable, and for test part we have features matrix and output and target variable values vector. Of course, we could use the default function to split the dataset, but I wanted to show an example of using the ilog and indexing again. Since further the same actions will be performed with different models, it is worth formatting the code in a function. The first function performs the cross-validation process. Splitting into 5 different sets was used, and to do it, we need to use cross-val score function and point out scoring matrix, accuracy matrix. We use root mean squared error. And we can print result on validation set -1 because this process use negative root mean squared error because process of training models in this function is considered as process of maximization. And about the same code for print mean -e on validation set. And to calculate accuracy on test set, we can use fitting and testing model on the whole training whole dataset. And I use the function to calculate performance metric calc-ms-e, and after fitting, we need to return trained model. Let's define the function for calculating RMSE of model. The function predict returns model prediction model output for input features. So in this code, we calculate mean squared error as error between model predictions and actual value, and to calculate root, we apply the function sqrt. And the next function for visualization result. Create object for visualization. Define time steps. And we can copy and paste these code as sample. But we need to modify it. So this function will demonstrate actual generation as G, green lines, and prediction of the model. And for predicted value, the color is blue. Okay, we finished preparation step, creation function for calculate error, for create and evaluate model using cross-validation approach, and for visualization prediction of our model. Now we can start to working with models. The first model is linear regression. Using this function, we can create model and apply cross-validation. And visualize. I think that name of function should be verb. Okay, let's first of all test this code, and probably we should do fix mistakes. Yes, first of all, we should fix this. Imagine yesterday this code worked, but today this matrix has been removed from the library. Okay, let's do it ourselves. We can use this metric without root and calculate root using NumPy. Okay, let's check it again. It was just typo. Okay, and additional my mistake with function names. And I think the next mistake is that we need to apply show function to this object. Okay, great. Now we have the output results. We have values of accuracies and this chart to analyze errors. And you can see that accuracy is quite low, but at the same time, variance is very, very low because accuracy, root mean squared error on validation sets and on training set are about the same. It means that this, the simplest model, has very low overfitting, but we can conclude that we have underfitting and we need to increase complexity of model. But for linear regression, we cannot increase the complexity, so we can select another machine learning model. For example, decision tree or regression tree. And for decision tree regressor, we can specify maximum depth of tree. Let's start from low value. Okay, and now you can see that we improved quality because now error is lower, but we have little variance. And now we can conclude that we can try to increase the model complexity and again. But now you can see that our variance or difference between accuracy on validation set and test set now is quite high. It means that now we have overfitting. And we can zoom to show errors on this set. Okay, now we can apply ensemble methods. We can start from random forest. And we need to specify number of models of trees, for example, 10, and max depth of each tree. The accuracy has become higher since the RMSE is lower, but there is a noticeable difference between the accuracy of training set and the assessment results using cross-validation. This indicates the overfitting. We can try to manually select parameters of weak models and parameters of random forest to improve accuracy and to decrease variance difference between error on validation sets and training sets. But of course, in real-life applications, there are several approaches. For example, grid search, it allows us to define number of parameter values and check all of them, all possible combinations. And another approach is random search, when we define only range of each parameter, and then this algorithm select combinations of parameters randomly and check all these combinations to select the best combination of hyperparameters. Or we can apply more complicated techniques, for example, genetic algorithm or swarm intelligence algorithm to optimize to select hyperparameters of machine learning models. Okay, and additional combination of parameters. So let's try to use adaptive boosting now. And for this model, we need to point out base estimator, for example, decision tree regressor with max depth, for example, 5, and count of models, count of weak models or estimators, for example, 50. As you can see, now we have good enough error, but high difference between training set and validation set shows that there is risk of overfitting. We can decrease complexity of weak models, but in this case we increase error. And we can try to increase number of individual models of ensemble. So as you can see that accuracy of AdaBoost regressor and random forest are about the same, and the most important thing is parameters of individual weak models and parameters of ensemble algorithm. As you can see, there are several additional parameters, as for AdaBoost regressor, also for random forest, and for decision tree regressor, there are a lot of hyperparameter, and we need to select near to optimal combination of these parameters. Okay, let's finish our experiments and let's test our model, for example, AdaBoost regressor with these hyperparameters on test set. And to do it, we can visualize model, but using test part of dataset. Okay, and of course we need to calculate error. We can use this function and point out model and test part of dataset. Now you can see that this error is about the same as we have on training set. For validation set, the error is higher. It probably means that test part of our dataset contains less count of difficult situation for forecasting, for prediction. The last point is saving the model to a file. After all, we don't want to retrain the model every time. We need to be able to save the trained model so that we can use it later. To do it, we can use this library and import the function dump and load. Now we can just save the model to a file. Okay, and now you can see that we have this file, and it means that we can download it and use it later. To load a model from the file, we need to use the function load. Let's check it. And we can now use these loaded from the file model to test. As you can see, model after loading from file gives us the same result as the initial model. Thus, today we considered tools for visual data analysis, cross-validation approach, scikit-learn library for machine learning, and regression models such as decision tree and ensemble models. Thank you for your attention.